Hello everyone, welcome back. In this video we're going to go through an example of completing an ANOVA test. Okay, and so you'll see the computer output that we're going to look at, or that you'll be looking at regularly, and you'll get to see how I want you to go through each step. Okay? As a side note, each of these steps is expected when you complete an ANOVA, just like it was when you complete a 2-sample or 1-sample t-test or a z-test or a interval for p or an interval for mu, so on and so forth. I expect all the steps that I show when you do the work. Okay, so just get that out of the way right at the beginning. Okay, we have 5 samples here, and they're made-up samples. I generated them for a certain purpose, and so there's no sort of backstory that goes with these samples. They're not of any sort of concentrations there. So there are the 5 groups. I'm going to set the significance level to be alpha equal to 0.05. Okay, so that'll be given in the problem as usual, but you always need to put it down as part of your analysis. And then the hypotheses that we're going to be working with are the null hypothesis that all of the group means, group 1 through 5, are equal. And then the alternative hypothesis that at least 2 of the population means are different. Okay? You can always write that specific alternative hypothesis there. You don't have to give it in terms of mathematical symbols like I did in the last video, but you can if you want. Okay, so either is fine. The assumptions of the test, we have 3 of them, really 4 of them, but we're going to check 3 of them: normality, equal variance, and randomness. The samples come from some type of randomization. Okay, so here are the 5 QQ plots, 1 for each of the samples. Okay, there are a lot to look at, but you'll see that all of them fall fairly close to the line. Okay, you'll see that in some there are some deviations, okay, right at the end. But when you have a smaller number of points, you're going to see a wider number of the points will vary from that line more. Okay, so in the example that I gave in describing a QQ plot, we had 100 points, which is not a ton, but is a sufficient number that any significant deviations from it would raise an eyebrow. But each of these have 20. Okay, each of these have 20 samples, and so it's possible with 20 samples to see those larger variances. Each group, though, does follow, at least in the middle, follow along with the line fairly well. And so we're going to go ahead and assume normality. Right? It turns out that ANOVA is what the book and what most people call resistant to outliers, or it's a robust method. Okay? Not just to outliers, but it's resistant to breaks of normality. Okay, so even if the populations can't be assumed normal, that doesn't mean that the ANOVA is bad yet. Okay, so there are the assumptions. There are the QQ plots, and we're going to assume that normality is met in general for each of them. Even if it's not, I'll ask you to move forward for the reasons I just droned on about a few seconds ago. Okay, so normality, great. What about equality of variance? So in practice, I'm just going to say that I want you to assume this. Now, there are many ways to actually check equality of variance. Okay, or some people call that equivariance. There will be many different names of that. Okay, I'm going to give you here, for just some purposes, for just kicks, a density plot of each of the samples. Okay, and so for this you can get a very rough idea if equality of variance is a assumption that we should think about. Is it violated or not. Okay, and so you'll see this again. There are only 20 points to make these plots, and so it's going to be a little odd. Okay, the density plots look a little weird. Some of them have multiple modes, so on and so forth. But you'll see that they do have slightly different shapes. But we're going to still assume equality of variance. Okay, they aren't totally different, and also I generated the data with equal variances or equal standard deviation. So in this case, it is true that the populations had equal variances. And so you'll see, even if the population actually does meet the assumption, usually we don't know. And we just have to assume, or we can check like we do with the normal QQ plots. Okay, even though it is actually true, we can still see with small samples things like this. Okay, which would make you step back and probably rethink whether the variances are equal in the populations. Okay, all right. So there's that, and then lastly, samples randomly taken. We'll always just assume that that's true. Usually it'll be described in some way in the description of the problem where the randomness is. In this case, I did take random samples for each group. And so you can rest assured that all three of these are met. Okay? And the fourth one that I don't mention here, independence, is also met. Okay? And you'll just sort of assume that those are true. It'll say something about that in the problem. Okay, so now we get to the important part, which is the test statistic, the p-value, the decision, and the conclusion. Okay, so here's the R output that you're going to see. Okay, it'll be different for each problem, of course, but it's going to have this general form. Okay, it looks like a table, and in fact, this structure that you see is called an ANOVA table, okay, where it has the DF sum SQ, mean SQ, F, and then P. Okay, this setup is called an ANOVA table and is used for other things than ANOVA in statistics. Okay, but we're only talking about it, of course, with ANOVA. And so I could talk to you for a while about how all of this is formed. We know the degrees of freedom. We talked about how you calculate those, but we didn't talk about how you calculate the sum of squares. Those are the weird formulas that we aren't going to talk about. Okay, the mean squared is actually formed by taking the sum of squares divided by degrees of freedom, right? And then the F value is formed by dividing the two mean squares. Okay, so if you'll see 347.2 divided by 8.5 is equal to 41.02. So each of them sort of build on top of each other there. And then, of course, you compare that F value of 41 to the hypothetical F distribution with 4 and 95 degrees of freedom. And then you get that it is extremely unlikely to see that F value, so on and so forth. So the test statistic is 41.02. That's what I want you to write, okay? So when you're actually doing the problem, you'll be given the output. I want you to tell me what the test statistic is, and then tell me what the p-value is. Okay, you don't have to show any calculation there because it's in the output. You just need to tell me. Okay, and so you don't need to write less than 2e to the negative 16th. Okay, that 2e to the negative 16th is there because that's sort of the smallest number that the computer is going to hold before it just defaults to 0. Okay, less than 2e to the negative 16th. So we get a p-value. I said it's less than 0.00001, which is just very small. Okay, so it's clear from this p-value, it's much less than the significance level. We reject the null hypothesis that the means are equal. Okay, great. And then our conclusion is at the 5% significance level, there is enough evidence to conclude that at least 2 of the population means are different. Okay, and so that is an example of just running an ANOVA test. Okay, so at the end we get that there is a difference between at least two populations, but we don't know which ones they are. Okay, if we went back and we looked at the graph or the plot of the 5 groups, we could probably give a guess about which ones are different, but we don't know for sure yet. All right, so that's going to be the end of this video, and then I'll come back with one final video that talks about what multiple comparisons are, and then how to interpret the R output of the multiple comparison that we're going to do. Okay? I'll see you next time.